Chapter 9 is about quadratic functions. Now, if you remember, quadratic functions are functions that have a degree of 2, right? Remember the one question on the test where you had to label the, you had to put it in standard form, and then you also had to label it based on the number of terms in the degree. So quadratic has a degree of 2, okay? Which means that the largest degree of an individual piece of the polynomial is 2. So, when we're talking about quadratic functions, there's something called a parent function, okay, which is where all of the other functions are based off of. The parent function here is y equals x squared. Okay? So all of the other quadratic functions are based off of this parent function. In other words, we will do things to this function, such as maybe put a different coefficient here other than 1, or add something or subtract something on the end, things of that nature. And what that's going to do is that's going to change how this function would look to mimic or to move to our new function. So the first section of Chapter 9 talks specifically about the graphs of quadratics. If we are to graph this parent function, okay, what's going to happen is when we make our table and we pick some values, like 0, -2, 2, -5, and 5. Okay, we plug 0 in for x, 0 squared is 0. When we plug -2 in for x, -2 times -2 is a positive 4. When we plug 2 in, 2 times 2, or 2 squared, is 4. -5 squared is a positive 25, and 5 squared is a positive 25. So when we're doing this, what do you notice about the x values versus their y values? What kind of relationships do you see here? Okay, the negative and the positive x's produce the same y values, right? That's because we're squaring the x. Okay? And what happens is when we graph this, if we go ahead and graph these ordered pairs, okay, we've got 0, 0, -2, 4, +2, 4, and then 5, way up here 25, should be almost pretty much off the board, okay? And when we connect these, it's going to look something like this, okay? Or like a U shape. This is the parent function. This is called a parabola, okay? Questions so far? Something funny came in? Okay. So, when we graph any kind of quadratic, it's going to create a parabola. Okay, this is kind of a poor graph, but you get the idea. Now, our graphs can go where they point up or where they point down. Okay? And the difference between this and this, the ones that go up have positive coefficients here. Okay? Or in other words, the a value for y equals ax squared plus bx plus c, the a value is greater than 0. When the parabolas are graphed and they go down, that's because the a value, or the coefficient of the x squared term, is negative. Okay? So if it's positive, it points up, and if it's negative, it's pointing down. Now, there's some other pieces to parabolas that we want to talk about. If we look at any of these graphs up here, okay, we can draw a line right down the middle of them to where if we were to fold it on top of itself, it would go perfectly on top of itself, right? Almost like a mirror. In this case, right there is that line. Okay? And for all of these that I drew, it happens to be the y-axis. But this line is called the axis of symmetry. Okay? I think I spelled that wrong, but you get the idea. Now, the axis of symmetry goes right down the middle of our parabola, and if we were to fold the parabola on the axis of symmetry, it would go right on top of itself. Okay? And that's due in part because we are squaring the x. And when we square the x, we end up with the same y values. So it's like a mirror image wherever this axis of symmetry is. Okay? The other point that we want to talk about, or the other thing, in part, are these points here, or the highest or the lowest point of the parabola. That point is called the vertex. Okay? Now, if the parabola opens upward and the vertex is at the very bottom, then we can call that a minimum as well. If the parabola is opening down and the vertex happens to be at the very top, then we call it a maximum. Okay? And as I said before, when we're talking about the coefficient of the x squared, when it's positive it goes up. So if a is greater than 0, then we have a maximum because the graph would go up. If a is less than 0, then we're going to have a minimum because it goes down. Does that make sense? Okay. Are there any questions so far? Brendan?
How do you know if it goes down or goes up?
The coefficient that would be right in front of, like for instance, this guy might be y equals negative x squared, or this would be, or I'm sorry, this would be a positive x squared. And this one would be y equals negative x squared. Okay? When it goes up, it's a positive number in front, and then when it goes down, it's a negative. Okay? Now, the other things that can affect how our parabola looks. Okay? If we take this function right here was y equals x squared. This is the parent function. Okay? If we come over here and we say y equals x squared minus 3. Alright? And we go ahead, we want to graph it again. And the way we graph it is pretty much the way we graph anything. We make a table, and we pick some values for x, and we plug them in and get our values for y. So if we pick, let's use those same values. 0, negative 2, 2, negative 5, and 5. Okay? When I put 0 in for x, 0 squared is 0. 0 minus 3 means y is negative 3 here. When I put negative 2 in, negative 2 squared is a positive 4. 4 minus 3 is 1. A positive 2 in there. 2 squared is 4, minus 3 is 1. Negative 5 squared is 25. 25 minus 3, 22. 5 squared is 25. 25 minus 3, 22. So if I take these same ordered pairs here, these ordered pairs, and I compare them to those, we've got 0, negative 3, negative 2, 1, 2, 1, and then 5, 22, and negative 5, 22. Okay? So what do you notice about this new graph compared to this graph and their respective functions?
It just shifted down.
It shifted down 3. Okay? And that's because we put a minus 3 on the end. So just like when we're talking about slope-intercept form, okay, where the thing on the back moves it up or down, okay, it does the same thing with the parabola. If we put minus 10 there, then it's going to shift this whole parent function down 10. If we put plus 8, it would shift it up 8. Okay? Now the other thing that we can do is we can put a number in front of the x squared. We can put a different coefficient other than 1. And we know, after talking about it a few times, that if it's positive, it's going to go up, and if it's negative, it's going to go down. But if the number is other than 1, it's going to do other things. Okay? Let's try one of those. So let's say we have y equals 2x squared. Okay? So I'll pick some values for x and make a table. Okay? So when I put 0 in there, 0 squared is 0, 2 times 0 is 0. Negative 2. Negative 2 squared is 4, 4 times 2 is 8. 2 squared is 4, 4 times 2 is 8. Negative 5 squared is 25, 25 times 2 is 50. 5 squared is 25, 25 times 2 is 50. So when I graph this guy, I've got 0, 0, negative 2, 8, positive 2, 8, and then way up there it would be 50. Okay, 5, 50, and negative 5, 50. So what's going to happen is my graph's going to look like this. Now, what do you notice about this graph versus our parent function?
It's skinnier.
It's skinnier. Okay? Y equals x squared looks like this. Y equals 2x squared is a lot skinnier. So, if our coefficient in front of our x squared term is greater than 1, it makes it skinnier. And the bigger the number, the skinnier it gets. Okay? If it's less than 1, what do you think is going to happen? It'll get fatter or wider. Okay? So if there's a fraction or a decimal number out there, it's going to get wider. Does that make sense? Now that is shown on the top of page 548, problem 3. They give you 3 different graphs there, and you can see that the third one all the way over on the right is the parent function, y equals x squared. The one in the middle is y equals 1/4 x squared, and you can see that that's quite a bit wider than the parent function. Then the one on the far left is y equals negative 4x squared. And you can see that the negative makes it go down, and the fact that there's a 4 for the coefficient makes it real skinny. Okay? Now, when we're graphing these parabolas, okay, we can use the knowledge that when we put something on the back, it either moves it up or down. Okay? And when we have a coefficient other than 1, it either makes it skinnier or wider. Okay? We can use that to see what a different graph is going to be compared to the parent function. So if I asked you, okay, what would this graph right here look like compared to the parent function of y equals x squared?
Be skinnier.
It would be skinnier,
And it would go down.
and we would shift it down 8. Okay? So if you just had to do a quick little mock-up of what this might look like, you could go down 8, and then since it's 5, that's going to make it really skinny. Okay? Because 2 made it pretty skinny. 5 is going to make it really skinny. So it's going to probably look something about like that. Okay? Just if you had to sketch something of what it might look like. Okay? That's what problem 4 on the bottom is asking you to do. It's asking you to determine what are the differences going to be between the graphs of y equals 2x squared plus 3 and y equals 2x squared. Well, what's the only difference between those two functions?
It has plus 3 on that.
It has the plus 3 on the back. Okay? So what does that do for us? It moves it up 3. Okay? When it's positive, it moves up. When it's negative, it moves down. Okay? Any questions so far? Okay? So, Brennan, how do we graph these functions?
Get values.
Get values?
Pick values first.
Okay, we make a table and then we pick the values, right? And then we go ahead and plug our values in, get our y values, okay, and then we can graph our ordered pairs. Sydney, what does something on the end do?
Either makes it go up or down.
Okay, it shifts it up or it shifts it down. What does the coefficient of the x squared term do, Rihanna?
It makes it skinnier or wider.
Okay, it makes it skinnier or wider. Which one's which?
If it's bigger number, it's skinnier, and if it's wider, it's smaller.
Okay, if it's greater than 1, it makes it skinnier. If it's less than 1, it makes it wider. Good job. Okay, the last thing that we want to talk about today is the falling object model. Okay, and that's problem 5 on 549. You can see that the falling object model is h equals negative 16t squared plus c. So what we really have is a function here, a quadratic function, that's in the form y equals ax squared plus c. Alright? Where h is the height in feet, t is time in seconds, and c is the initial height. So, problem 5 says an acorn drops from a tree branch 20 feet above the ground. The function h equals negative 16t squared plus 20 gives the height h of the acorn after t seconds. So you can see that they have already subbed in 20 for c because the branch is 20 feet above the ground. That's the initial height. Okay? Now it says, what is the graph of this quadratic function? At about what time does the acorn hit the ground? So we can see that the coefficient of the x squared term, or in this case t squared term, is negative, right? So we know that the parabola is going to be pointing down. Okay? And if you look at the graph that they provided, you only see half of it. Why do you think that is? Titus, why do you think that we only have the first quadrant of the graph?
You can't go like negative seconds.
Exactly. Because the x-axis is representing time, and you can't go back in time, at least not yet. Okay? So we have to start at 0, and we don't need to represent any negative values there. And you can see that on the graph, it starts at 20, and it goes all the way down to 0 feet for the height. So how long, based on the graph, would it take an acorn to hit the ground? Right, a little over 1 second. Okay, from 20 feet. Now, you can use this, the falling object model, for just about anything to get a rough idea of how long something's going to take to hit the ground. And I made a comment yesterday in the other class about dropping a bowling ball versus an acorn. And Logan thought that the bowling ball would land first. What do you guys think?
It
Wouldn't? Anyone think it would? 16-pound bowling ball versus an acorn?
Falls at the same rate.
You think it falls at the same rate?
Yeah.
Even though one of them weighs a bunch more?
Yeah.
Why do you think that?
Isn't that like some mathematician did that a long time ago?
I got a ball here. I've got another ball here, right? Now this one, tell me how much more you think that one weighs than this one? About 3 times as much, maybe?
Yeah.
All right. If I drop them, they land at pretty much the same time, right? But this is something the same size. What if we were to get something heavy like a bowling ball and something like an acorn, such as this Hershey's Kiss? Do you think these are going to land at the same time? Exactly the same time. Now we were doing this with all kinds of stuff yesterday. I had my keys, dropping keys. As long as they have the same starting height, they end up landing at the same time. What's that? I don't know. But what about this piece of paper? Okay, so why does the paper in the acorn, or the paper in the ball, or the paper in whatever, fall at a different rate than one another? Justin?
Paper causes air friction and slows it down.
Okay, the paper, air friction or drag, right? So the paper catches the air and floats down, whereas the other objects that we were dropping cut through the air a lot better. Okay? Any questions about any of this? Okay, good. That's it. Homework. Page 550, numbers 8, 16, 18, 20, 30, 34, 36. Bonus is 42 and 44.